All right. So, welcome to the pilot session of MedML. You should see my screen. Is it a little bit too small, Avinash?
It's still that like half size, but
Is it better now?
it's full now. Yep.
All right. Let's do this. All right. Okay, great. All right, so welcome everybody to the pilot session of MedML. It's 11 a.m. today. We're planning on having the general session in a week. So this is a little bit of a setup for that general session, but also trying to teach some real machine learning at the same time. All right, so what is MedML? First of all, since everything's Twitter now, we're gonna be using this hashtag. So I expect to see at least 2 or 3 tweets related to it. But the whole point of this MedML is to bring in machine learning concepts into medical school, specifically Emory's medical school, specifically related to discovery. Some of y'all are M3s, M4s, and have already gotten the discovery talk. There's a specific talk in discovery that does the basics of statistics. It does some very basic things about sensitivity, specificity, t-tests, that kind of stuff. There isn't a similar curriculum for machine learning, and that is, I think, a major gap in setting up medical students for success in research. So this is a student-led initiative to try to bring in cutting-edge learning techniques into medical school to teach machine learning. That's pretty much it in a nutshell. We're going to be relying heavily on 2 things: medical examples. We want to focus and anchor things in medical examples, and then also have interactive open source Python notebooks. We're going to be using things like Jupyter notebooks and Colab. So those things might sound familiar. If they don't sound familiar, don't worry, we'll cover it. We're going to take an approach where we actually simulate data from pretty simplified open source models from first aid. You know, there's something like the Coagulation Cascade has different components to it. Each of those components relates to each other. We're going to set up models for those, generate data, add a little bit of noise, and then use different machine learning approaches to try to tease apart the model, the kind of understanding that generated the data. This lets us focus solely on the machine learning component of it, and also lets us critically assess how well these different machine learning algorithms do in actually letting us understand what's generating our data. So the goals of the pilot specifically are, it's going to be abbreviated for folks with prior experience. We're not going to spend as much time discussing code. We're not going to spend time discussing why machine learning is important. These kind of things we'll have a dedicated presentation for next week in the general session. But for today, we're going to dive right into the notebooks and the examples. The 2 notebooks that we're going to focus on are multidimensional regression and testing training splits. We'd like to cover these same things in the general session, but depending on your feedback, on the pilot group's feedback, we might actually move from our multidimensional regression into a simple linear regression notebook that's set up and ready to go. It's just a little bit ambitious maybe to start with multidimensional regression. We're going to rely on your feedback to know whether we should dial that back down to a simple linear regression example. And then get feedback from y'all for next week's general session. Just general feedback, any ideas you have. We'd love for y'all to get involved. Also, this is purely student-driven, open source. The goal is very much to put tools out there that enable medical students to do really cool machine learning. And today's session is going to be a little bit more conversational. So feel free to chime in. I'm going to ask Avinash or Alex to kind of field questions. So maybe type something in the chat, and then one of those 2 can interrupt me just to keep the flow going. But this is a small enough group that I think I'd be fine with anyone just chiming in whenever. Just, I know Zoom does a little bit weird stuff with how audio is prioritized, which gets to the last point. These are workshops. These are not meant to be lectures, but given the Zoom format, we're going to have to find some middle ground. I think we're all really looking forward to things opening back up and us being in person in the computer lab in the School of Medicine, with everyone having their own instance of the notebook open, tweaking with all the widgets, and having a more workshop style session that's the goal, but in the meantime, we'll try to do the best we can to ease into that process. But today should be a little bit more conversation. So what is machine learning? Well, there's a lot of different figures like this, but this typically captures most of what people consider artificial intelligence, machine learning, neural nets. All these different buzzwords kind of fit into this Venn diagram where machine learning is a subset of artificial intelligence. And inside machine learning, there are different ways to actually implement learning. What is learning? Learning pretty much amounts to patterns. We want to identify patterns. And as scientists, we may be more interested in specific patterns, patterns that are causal, patterns where something causes something else, but they're still patterns nonetheless. So typically, we rely on very carefully constructed experiments to isolate and statistically validate simple patterns. This is the standard way we're taught. Find a hypothesis, make the null hypothesis. What would your data look like if there wasn't a relationship between these two variables? And then collect a large enough sample size to say, yep, I can confidently reject the null. There's something going on here. Or I can't reject the null. I can't say that there's, nothing going on here. Clinical research is a lot messier, and machine learning provides a rigorous way of actually coming in and tailoring your analysis and your statistics to the data set you have available. It's a way that you can rigorously identify complex patterns in your data, regardless, but also limited by how well the data was collected. Machine learning is, in a nutshell, a way to find patterns, simple or complex, in data and then verifying that it's there when you are forced to do so and you can't go back and do another experiment. That's kind of the way I see it. There are 50 million different perspectives on machine learning. I'm eager to hear everyone's perspective for sure. We'll save that for the discussion. But overall, machine learning is kind of this alternative approach to finding out what's happening in our data. Okay, so the outline for today is going to be, we're going to do a quick overview of Colab and Jupyter. These are pretty much notebook programs built on top of Python. So Python will be the common theme in all of this, but we won't spend too much time diving into the code. We'll have a brief intro to coding in the context of these notebooks, but again, we won't spend too much time on the coding. The goal of these workshops are to get you ready to deal with the notebooks yourself offline and empower folks to engage with the Python resources that are out there. We'll start with multidimensional regression. What is that? Why is it the foundation of machine learning algorithms? We'll discuss testing and training, this kind of other approach to inference in machine learning that's actually a powerful tool for us to make sure the patterns we find are actually there. And finally, we'll end with discussion and feedback. This is a nice little funny XKCD cartoon of all these different curve fitting methods. And today we're going to really focus on just one small quadrant. It's not a quadrant, it's a whatever tent. Just the top left. We're going to focus on linear regression. Just know that there's a vast, rich world of curve fitting methods. And curve fitting is just one tiny slice of machine learning. Our goal is to build up to a point where we cover all the foundations of machine learning and then just really hone that down as a curriculum for the med school. And then empower students to, again, go to the many, many resources that are out there that can actually solidify a lot more of the advanced topics. Okay, we're not quite to parting thoughts yet. So we'll go ahead and dive in. If there's any questions right now, just go ahead and put it in the chat. Avinash, Alex, are we good to go?
Yep.
Great. All right. So do all of y'all see this notebook? Cool. Is the font too small? Is it too big?
Do you want to zoom in just a little bit?
Yeah, I'll try to. It should work. Is this working?
Yeah.
Yeah.
Awesome. All right, great. So for today, we're going to do screen share on this workshop, on these notebooks. I'd like to get folks' feedback on whether this is a good procedure to go with the general. I think it's going to be. That being said, the alternative is to actually send out the notebooks ahead of time and then have folks interactively work with us as we go through the notebooks. The second one makes a lot more sense when we're all together in person, because there's a way we can walk around the room and anchor and answer people's questions. Given the Zoom format, I'm suspecting we might need to do a screen share version first, but we'll go ahead and we'll do the screen share version right now. And then after the session, either today or tomorrow, send out the links to the notebooks that we have available so far to get y'all's feedback on it. Okay, so the first one we're going to be doing is machine learning, intermediate linear regression, really the gateway to machine learning. All of this is going to be open source, so we put our license in there. And it's an open source license, GPL3, for those that it makes sense for. So, okay, let's do a quick overview of what linear regression is. Linear regression is the workhorse of science, really. It's how we do this pattern recognition of whether variables affect other variables. So here you'll see a pretty simple plot of just a silly example of eggs deliciousness and an eggs cooking time, okay? So on the x-axis is the cooking time, how long you actually cook the egg. And on the y-axis is how delicious the egg actually is. So let's say we got 100 eggs and actually ran this experiment. And those 100 eggs correspond to these red dots. We want to know, is there a relationship between how long I cook the egg and how delicious the egg is? What we can do is we can rely on linear regression. We can say, you know what, is there a pattern here? I want to see if there's a pattern here. And I want to fit a line to find that pattern. And I want to see how good that pattern actually is. And what we find is if we focus only on 0 to about 6 minutes, you'll see that there's a pretty solid line. And that line tells us the more we cook the egg, the more delicious it is. That's fantastic. That's science right there. We extracted understanding from this data set, and we have this understanding that cooking is somehow related to deliciousness. Now, the rest of the curve is there on purpose. Linear regression comes with it a lot of limitations. Linear regression assumes exactly what's in its name, that things are lines. So when you have relationships that aren't quite lines, in this case, there is a limit to how long you can cook the egg. And then after that, it actually doesn't taste that good. It tastes rubbery, it tastes burnt. So linear regression is good for little pockets where you can reasonably assume that the relationship is aligned, but outside of that, it starts failing. That blue line does not do a good job of predicting how delicious an egg is if you cook it for 15 minutes. A lot more of the advanced machine learning techniques we'll learn in later workshops, much later workshops, is going to be nonlinear approaches to understanding data. So linear regression is the gateway, but there's a whole slew of powerful techniques in machine learning that do nonlinear curve fitting and then also nonlinear learning of the underlying relationships that are in our data. So for today, what we're going to do is we're going to focus on code setup. How do we get set up with these this Jupyter notebook, this Colab notebook? And then how do we do some pretty straightforward linear regression on a multi-dimensional data set? That data set is going to be a simulation of the coagulation cascade. And then we're going to do a regularized regression. So we're going to introduce the concept of regularization, which is really the first, is one step into machine learning. It's one step into some of the more advanced techniques that let us do some really cool learning. And then we'll kind of train our model and we'll validate our model before moving on to the next notebook, which will be focused on training and testing. Any questions so far? I think we're good. Okay. So a brief introduction to what we're looking at here. So where we are right now is we're in Colab. So Colab is Google's new initiative, relatively new initiative, at least for some of us, new initiative to actually do online notebooks where the notebooks run on their servers and are delivered to us. Notebooks are just nice front ends for Python code. So all of this text is written in Colab. It's written online in my browser. And the code that is in line with the notebook is Python code. So this may look familiar to some of y'all. It's okay if it doesn't. But Python code comes in, lives inside of our notebook, and we can actually run the notebook. We can run the code inside the notebook, and it outputs figures directly into our notebook. This is somewhere in between a document, like a publication, and actual code. So being able to do both of them together is really what enables initiatives like the one we're trying to do right here. So Colab is online. It's freely available to everybody. These notebooks that we'll be working with and that others work with can actually be downloaded. So you can go to File, you can do download IPYNB. This is an interactive Python notebook. When you download the notebook, you can run this notebook in a local version of a notebook server called Jupyter. So I do have a Jupyter notebook session open. We can maybe cover that a little bit more in the discussion if we need to, but imagine Colab, but imagine imagine Colab, but imagine can y'all still see the notebook?
Yep.
Okay, so imagine Colab, but it's all on your local machine. This is going to be an important concept because Colab, I don't believe, is HIPAA compliant. So if you're wanting to use this code in your own data, you got to be really, really careful, / just don't do it on Colab. Download the notebooks and run it on a local Jupyter server. That may mean nothing, but we'll actually, next Saturday, we'll have a general session that'll be more like this. It'll be a little bit more lecture style, unfortunately. But we'll try to have it be a workshop. And then on Sunday, we're aiming to have quote unquote office hours where we help folks get set up with Jupyter on their local laptops. So hopefully that gives a general idea of what notebooks are. In a nutshell, it's Python included with beautiful text rendering. So it lets us have documents that have the best of both worlds. So the way you'll see in our notebooks, at least, the code actually split up is you'll see general imports. So these imports are our way of building off of the brilliant work that others have already done. These single lines, import NumPy as NP. NumPy is a massive library that's all about working with vectors and matrices. With that one line, we have access to millions of lines of code and millions of hours of hard work at our fingertips to do our job. So coding is a very powerful approach to building up the tools that we need for our specific goals. I won't belabor that here, but it might be something that we want to stress with the general group is coding is a powerful way to build off of the work of others and not sit here and reinvent the wheel. And you'll see a lot of other imports. So you can take a look at this to see which tools we're relying mostly on. The most important one that we will be relying on in this notebook is right here. It's the scikit-learn's library for linear modeling. So linear regression, Lasso, and ElasticNet, which we won't cover today. But these are 3 different approaches to linear regression, and we're relying on sklearn is the library. We're learning on sklearn's implementation of these linear regression approaches. And there's a few other things that we can cover in the discussion if we want to, but long story short, this block really tells us these are the tools we're going to be using in the rest of the notebook and gets things set up so that we can do that. So how do we get things set up? An important thing to know is you go up to runtime, and like I said, there's code in these notebooks, so you can actually restart and run all. What this does is it restarts Python running on Google server. It restarts the Python interpreter, the Python core program, restarts it, and then runs your code in your notebook for you. So we've been running this particular notebook pretty nonstop for the last 3 days, so I'm pretty sure it all works completely fine. But when we go and we click runtime and restart and run all, it restarts Python and runs the code. We'll do run all one more time just to make sure that the code was run and that the figures are plotted right. And then we can go ahead and we can get started. So we will ignore this code block. So one of the beauties of Notebook is we can actually collapse code blocks and have it go away if it's a little bit too much detail that we don't currently care about. And we can go ahead and dive right into the linear regression example. So right now, a lot of y'all are almost definitely familiar with linear regression. How do you fit lines to 2-dimensional data? We have an independent variable and a dependent variable. We run an experiment, we have data points. We just did an example, a silly example, but linear regression in 2 dimensions, pretty straightforward. How do you fit a line to this scatter plot of data? Where machine learning really starts helping us is when we have more than 2 variables, when we have many, many variables. For machine learning, for a lot of the machine learning algorithms, it's trivially easy to fit 2 variables. It's trivially easy to fit 100 variables. And so what we're going to do today is focus on the coagulation cascade, one of the more complicated examples that I think we're expected to learn in the first 2 years of medical school. And we notice that there are many, many components to the coagulation cascade. So if we didn't understand how the coagulation cascade worked, and instead all we had were measurements of each of these factors, how do we extract an understanding of the coagulation cascade is going to be the primary problem we deal with in this notebook and in a later notebook where we focus on dimensionality reduction. So we want to understand this through the data we collect from this model. Okay. Now, the first step to this is we want to translate this diagram into a Python usable model. And the first thing we do here is we set up a model of how each factor affects each other factor. And you can check out, so the code that generates this is above in the cell that I just collapsed, but we'll go ahead and we'll call it. We'll actually generate a coagulation cascade model. We'll find how the different factors relate to each other. That's what we'll call the adjacency matrix. And then we'll start diving into simulating the data and then actually doing a regression on top of the data. All right, so the coagulation cascade that we see, our version of it that we're going to work with looks like this. It's a nice, neat graph with each of the factors connected to the factor that it affects. And on the left, you'll see the pretty graph version of that. We call these networks graphs. And on the right, you'll see the adjacency matrix. So how to read the adjacency matrix is on the x-axis, you'll see all the factors. On the y-axis, you'll see all the factors. And anywhere that the 2 factors are connected to each other, you'll see a beige square. And so what this matrix conveys is the same thing as what the left figure conveys, and it's just which factors are connected to which factors, okay? All of this is to set up a ground truth. We want to set up a model of the coagulation cascade, generate data, and then add noise to that data so that we can use machine learning approaches to regenerate this understanding. We want to come back to this and say, I know which factors are connected to each other because the machine learning algorithm was able to find the connections between them and validate those connections. Quick warning, for the sake of this example, we're going to focus on PTT. We're going to try to focus on which factors contribute to PTT from measurements of the factor concentrations and measurements of PTT. For the sake of this example, we've gone ahead and we've zeroed out the common pathway. We're going to act like the common pathway doesn't contribute to the PTT calculation and move forward with that. That's more for illustration purposes for some of the regression approaches that we're going to do. But the beautiful thing about the notebook is once it's in your hands, you can go back and you can actually see how the regression approaches change when you include the common pathway into the PTT calculation. So there's a lot of text here. The text is primarily for folks when they're not in the workshop. So feel free to read these. We're going to be polishing them over the next week. We're not going to spend too much time here in the workshops discussing the text of it, but we do want to contrast the machine learning approaches with the bread and butter approaches that we are typically taught in medical school. So the way we're going to do things in the linear regression approaches are a little bit different than the experimental approaches. Our goal is not to do experiments where we isolate every 2 variable and see if they relate to each other. Our goal is to measure as much as we can from all the factors and then leverage the fact that there's structure, there are relationships between those factors that linear regression should be able to pick out. And we're going to extract those patterns from a data set and then see how well those patterns hold in a separate data set. Okay, So here's a little bit more mathy section. We will not go through these more complicated equations, but they pretty much boil down to we're setting up a linear model for how the coagulation cascade works. We're using that model to generate data, and then we're using linear regression to try to go from the data to an estimate, to a guess, an educated guess of what model actually generated our data. So all these three equations up here are the actual models that generate our data. And the specific equation we're going to be dealing with is down here. This might be worth visiting. It's the PTT is going to be a specific combination of each of our factors. We're going to take factor 12. We're going to multiply it by 3. We're going to add it to 2.4 times factor 11. We're going to subtract out 2 times factor 9. And then we're going to add 3.4 times factor 8. And include a little bit of factor 1. We're going to subtract 2 times factor 1. So this is the equation that is ground truth. And this is going to be used to generate our data. And our goal with linear regression is to come in and find out what these numbers are. We're going to find 3, 2.4, 2.0, 3.4, and minus 2.0 from the data. The beautiful thing here is this may be too mathy. This may be too overwhelming. So we'll go ahead and we should be able to collapse it, but we're still working through some of Colab's quirks. So imagine all of that collapsed, and we're going to focus solely on the linear regression itself, okay? So focusing on the linear regression, our first code block is here to generate our data, and we're going to generate about 10 patients worth of data, okay? And what this data corresponds to is for 10 patients, we're going to get concentrations of each of the factors. And we're also going to get 10 measurements of PTT associated with each of those patients when we collected those factors, okay? So the next code block plots this. So our plots look like this. This might be a little bit too big, so I'll make this a little smaller. So this is what our data looks like. This is our raw data. And on the x-axis in your left figure, you'll have patient number. And on the y-axis, you'll have factor concentration. For the sake of this example, we've already zeroed out the mean. So you'll see negative factor concentrations. Those aren't actually negative factor concentrations. They're just the fact that we took all of our data and we subtracted out the mean so that we could do some simpler linear regressions. The way to interpret this is sometimes with certain patients, you'll see low factors and sometimes you'll see high factors. And for that same patient, if we look at patient 4, here are how there are concentrations of each of the factors. And over here, you'll see the PTT that's associated with that combination of factors. So for each of these patients, you'll on the right side see the PTT value associated with each of those factors, combinations. Again, this is ground truth. This is from the equation we just covered, but it also includes a little bit of noise. What noise is it's that little bit of jitter you always have in every measurement. If I was trying to get the temperature of Atlanta right now and I called up 10 of my friends and asked them to tell me what temperature their phone told me, you'd get a little bit of a range. And that is noise. That's measurement noise. That's a little bit above, a little bit below, trying to get at what the actual temperature in Atlanta is. Same kind of thing here. The PTT value is going to be a combination of these factors, but then it's going to be a little bit of noise, a little bit of jitter around the actual PTT value. Our job with linear regression is to find the relationship despite the fact that that noise exists there. So this is a particularly important code block. Here, we're actually setting up a regression. And what this regression does is it says linear regression. We're going to fit our intercept, which we don't necessarily have to do, but for the sake of argument and for the sake of people's data, we're going to say true. You're going to get the slope. You're going to see how each of these factors relates to PTT, but then you also see if there's an offset. And the fit component of it is where the algorithm does all the work. Fit is what tells the algorithm, connect my x's, this left plot up here, with my y's, this right plot up here. Take this combination of factors and link it to the associated PTT, fit them, find the slopes, find the linear model that actually links these two. And once you found that model, you put it into this variable called REG, which is just named for regression. And what we're going to do is we're going to see how well this fit procedure actually found out the true model that generated our data. So down here, you'll see the true model is in blue. These are the numbers that I just told you about in 2 cells ago. We have something around 3, something about 2.4. We have -2. We have 0. We have positive 3.4. The blue line corresponds to our true model, the model that we actually use to generate our data. And the orange line corresponds to the linear regression model that the model found, that our very basic machine learning approach estimates is in our data. And you'll notice that it overall kind of gets the general shape, but it also misses some key factors. One, every single factor is considered important enough to include in the regression model. So you'll see even factor 10 actually has a -1, -0.3 or something. It includes factor 10's concentration in figuring out whether the PTT, figuring out the value of the PTT. Where it gets really problematic is that factor 5 is also included into this calculation. And these other things like surface contact and what is TT is I think the thrombotic cascade. These other factors are also included into the model when we know that they're not actually there in the model generating our data. So this might be a good time to clarify real quick. There's one model that's generating our data. This is the truth model. And there's one model that we just learned from the linear regression. That's the linear regression model. That's us trying to figure out what the truth is. And we're trying to do it with all the factors. We're not focused on this is essentially a hypothesis. We're trying to generate a hypothesis from our data set and say that hypothesis, that multidimensional hypothesis, here we're including 13 factors, that 13-dimensional hypothesis needs to be as close to what's generating our data as possible. And the long story short of this figure is we're kind of there, but we're kind of not. We actually have major problems in our model that make it far, far away from what the truth is. So this is kind of a problem. One of the reasons why we have this problem is we only have 10 patients worth of data, and we have 13 variables that we're trying to study. This is what we like to call underfitting. We have a lot of variables that we're trying to figure out, but we don't have enough data to fit those variables. Imagine trying to fit a line through a single point in a plane. You can do many, many lines. You need at least 2 lines. You need at least 2 points to fit one line through it. If you're trying to fit a surface or a plane to a 3D volume, you need at least 3 points to do that. If you only have 2 points, you have a lot of possible solutions. That's what this linear regression just found. It found another solution that fits the data, but it's underfitting the data. This is where regularization comes in. So regularization is this idea that we can systematically and rigorously introduce knowledge that we have into the regression algorithm itself. In the linear regression we just did, we literally said, here's the data, try to find the pattern in the data. Regularization is this powerful concept that you can actually introduce constraints to the model. We could go to the linear regression, we could cherry pick. We could literally cherry pick. We could say, you know what, I know the truth is that this coefficient and this coefficient are actually 0, so I'm gonna ignore them. I'm gonna cherry pick the coefficients that do what I know is true. When you actually know what the truth is, that's relatively not problematic, but when we're doing science, we don't know what the blue curve is. So cherry picking is a huge problem. All it does is serves to reinforce bias. What we can do with regularization is not cherry pick specific coefficients, but we can tell the regression model, hey, I know that most of the coefficients in the model you learn should be 0. I know that very few of my factors actually contribute to the PTT. That's all I'm telling you. I'm telling you to find me a model where a decent number of coefficients are 0. And if you have a non-zero coefficient, if you have a coefficient that you're saying this factor is important, it better be very, very important. Only include a coefficient if it is really helpful to actually fit the data. So that's where regularization comes in. So the one algorithm that we'll cover today is the Lasso algorithm. So Lasso is a regularized linear regression. It's you doing linear regression, but you telling the algorithm, don't bother me with models where every single coefficient has some value associated with it. Tell me models that have a lot of zeros in them. I'll let you put the zeros where you think they're right, but give me a model that has a lot of zeros. And how you discourage those zeros is this alpha coefficient right here. So with Lasso, we call a linear regression model, but we also tell it, you know what, I'm going to discourage you from including all the factors. And then I'm going to do the exact same procedure. I'm going to fit the data that we just saw up there with our factor concentrations and our PTT. I'm going to let you fit that data and then tell me what your model looks like. So we're going to go ahead and do that. So this is where we start getting into some of the interactive components of these notebooks. We have the ability to, alpha is a knob. Alpha is something that we can actually set. And if we were publishing this, alpha would be something that we would explicitly, transparently say. We would say, we found this model on this data with an alpha of about 3.4. So that's a way to keep yourself in check and keep yourself accountable. You're not cherry picking, you're telling the algorithm, find me a model with certain properties that I know should be true. So we're going to do that right here. So same thing. Let's look at our x-axis and y-axis. X-axis here is our factors. The y-axis is the coefficients, how important each of those factors are in calculating the PTT, and also the coefficients, the actual values you have to multiply each of the factor concentrations by to get the PTT. So in blue, you'll see the true model. This is the truth that we have the equations for above. In this kind of hazy orange red, you'll see the standard linear regression model we just learned above. You'll see how it kind of matches the blue, but also goes way off in certain factors. And finally, the new component is Lasso, the Lasso learned model. Right now, it's pretty bad. It actually looks even worse than the linear regression model. But that's because we're setting an alpha that's really low. So when our alpha is 0, we're not discouraging the algorithm at all, and it pretty much looks like the linear regression. The algorithm that runs looks a lot like the linear regression that we do. When we start moving this alpha up, when we start doing it a little bit slower, so let's do something like 0.33. You'll see that the green just shifted, right? The green shifted to be a lot closer to the blue than it just was, but it still pretty much just looks like the linear regression. If we increase the alpha a little bit more and start discouraging 0 a lot more, let's say we're going to do about 7. So we're at this arbitrary level of discouragement. You'll see that the green is actually starting to fit the blue a lot closer. What this is doing is it's discouraging non-zero coefficients. So a lot of these small coefficients that popped up in the linear regression are pushed down to 0 because they're just not worth having. They don't really do a good job of fitting our data. And as we scoot that up, we'll see that nothing comes for free. So at a certain point, when we start really discouraging zeros, you'll start seeing our good coefficients, the coefficients that were actually matching factor 8 and factor 1, you'll actually see them shrinking a little bit. So this alpha gives us the ability to discourage zeros, but it's not magic, that we have to be careful with it to actually tune it right so that it doesn't incredibly discourage coefficients. And so why this is an introduction to machine learning is that alpha, you can let the algorithm sweep through different alphas and find the alpha that best accounts for your data without overfitting or underfitting it. So if we move our alpha all the way back down to 0-ish, you will see this really, really awful model. And if we move it up to about 10, we'll see a green model that does a pretty decent job of capturing our truth. Keep in mind, we don't know that truth is here. We don't actually know that the blue line, how the blue line looks. So what we're going to do is we're going to say, we did two models. We did a linear regression model, and then we did a lasso model with our alpha about 11.79. And we're gonna say, you know, we found these patterns in our data, but we need to make sure that they're actually there. The best way to do it is to then take this model and see if we can replicate our findings. And one way to replicate our findings is to see how well these models predict a new data set that was left out, that we didn't actually look at. And for that, we're gonna set up a little scenario. We got really lucky. You know, a year later, we are able to redo this experiment, except this time we're able to collect 100 patients worth of data. Remember, we just had 10 patients worth of data. Now we have 100 patients worth of data. So we have two options. We can include those 100 back into our analysis and rerun the analysis. At this point, we probably have enough patients to just do a standard regression or a standard regression to figure out what the relationships are. But we have another alternative. We can take the prior models that we just generated and we can see how well they predict the PTT in these patients. Now, we've got these 100 patients. So the code down here just does a new generation of data. Here it generates 100 patients worth of new data. It takes the green model we just learned, the lasso model we just learned, and puts it in a variable that we can then use to predict on this new data set. And so these two lines go back to the models that we have. It goes to the Y predict, goes to the regression model we did, and predicts what the PTT should be from this new data set of factors. It doesn't look at this new data set's PTT. It tries to predict the new data set's PTT. And then we can actually then compare the prediction to the actual PTT that was collected. Down here, we're gonna do the same thing, but we're gonna do it with the lasso, the modified regression model, and predict on the exact same data set what the PTT should be. And then we're going to actually plot it. So this is the code for plotting it. One important point to make here is we had an interactive example up here with the lasso example. As we were moving the alpha around, we actually learned different models. We need to go down here and we need to rerun this cell. So each of these code blocks is called a cell. You need to rerun this cell to grab the latest green model that you developed and generate your results as a result of that. So you go over here, you go to the left and you click run cell. And when you do that, it reruns the cell and it updates the model that was actually learned in the previous cell. And finally, we come to the last point. And in this last point, I want to orient you first to the two figures that we have right now. So the best figure is on the left. Here we have our true measurement on the x-axis. On the x-axis is our true measurement. This is the PTT that we measured in our simulated 100 new patients. On the y-axis is our model prediction. This is the value that our model predicted to be the true PTT. And this blue line is what it would look like if our model was perfect. If the true measurement was 150, then our prediction should be 150 exactly. And so we should be exactly on that line. If our true measurement was minus 200, we'd want our prediction to be exactly minus 200. That's what's on that line. So one way we can judge how well our models perform is to see how they fall on that line. And so what I've done here is compared the linear regression output predictions, which you'll see in orange, with the lasso, which is in green. And what you should see is that the green is actually bunched up closer to the blue line than the orange is. Now, in this example, they're fairly close to each other. The orange has a correlation of about 97% with the true measurements, but the lasso does a better job. It does 99% on the predicted data set. Keep in mind, the models were not at all trained on this new data set of 100. So this is purely predictive power. It's, in a way, it's us doing a statistical validation. It's a statistical validation of our model in the context of new data. On the right side, you'll see pretty much the same data. It's the same data, except on the x-axis is the patient number. And each patient you go to has a true PTT value a linear regression estimated PTT value and a lasso estimated PTT value. So these two figures show the same data, but the left side should be a little bit more clearer in us assessing our models. So kind of closing remarks, what did we do here? What we did was we looked at the coagulation cascade as a model. We saw how its components interacted with each other, and then generated a data set that was simulated measurements of the coagulation cascade's factors and its PTT. We generated a data set, added a little bit of noise to it, and then used two different approaches to linear regression to try to understand how each of the factors related to the PTT. This is a classic regression approach where we're trying to look at multiple factors and how they map to a single PTT value. We demonstrated that linear regression kind of gets us most of the way there, but actually misses some key insights that we know about the coagulation cascade. We then used regularized regression to come in and insert a little bit of our knowledge into the model with a adjustable slider, essentially. And this enabled us to rigorously then validate these models in an entirely new data set to see how predictive they were in a new data set. All right, so
Vinny, just wanted to,
yeah.
Yeah, just wanted to add, so we had one question on interpreting a negative measurement on the graph on the left. Can you explain what that would be?
Absolutely. So this goes back to how we generated our data. When we generated the data, we then subtracted out the mean of all of our data, right? So imagine the factor concentrations are all positive. They're all between 100 nanomolar and 100 millimolar. The way these regressions work, it simplifies our problem if we just go ahead and subtract out the mean of the concentration. So a negative factor concentration is just negative from the mean that we found in our data set. It's just a normalized version of our data set. So that's how you're going to interpret these negative values as well. So the PTT similarly is zeroed out and the mean is subtracted out. So you'll see some values of PTT below the mean and some values above the mean. In a future example, we won't do a mean subtraction, and we'll have to adjust our regression approaches accordingly. But for the sake of today, we went ahead and we did that. Did that answer the question? Hopefully that answered the question.
Yep.
Cool. So it is currently 12 o'clock, and this was helpful to get an idea of pacing. We do have another notebook that we wanted to cover that was about training set and testing set. We will go ahead and cover it after maybe a little bit of a discussion or feedback for those of you that have to leave. If you can stay around, if you can stick around, please stick around. The testing and training set notebook is a lot more interactive, and we'll actually spend most of our time on a single example with multiple sliders to see how noise and how slope and how different factors come in and affect our ability to do training testing. But I do want to pause and see if anyone has any questions. Feel free to chime in with voice and video, or feel free to make a question in the chat. Just a reminder for some of the folks that entered in a little bit late, we are recording this mostly for internal purposes, just to get a clear idea of how this should run next week. But full disclosure, this is being recorded. All right, any questions? Any questions, comments, suggestions, anything like that? I would like to hear from folks. Was this too much? Was this too little? How is the pacing? What should we work on for next week's session?
Yeah, I have a comment.
Sure.
First, wow, good job putting together a lot of material here. This is like a whole class that you've got here, and it sounds like we haven't even seen the beginning of it. So good job. I really like the format of having like a workbook that people can download and play with. I actually, I kind of want to go through this workbook and like reference this video that you're recording and kind of work through it myself to really understand. And I think that would be having that resource available with the video and allowing people to work through it on their own pace would actually be a good learning method for everyone, especially people who are kind of new to coding and stuff. I think this is a lot, as far as for somebody who doesn't know what machine learning is and who has never coded. So I'm not sure. I think the hardest part will be like portioning it into digestible bites for the wide variety of people who are going to be at next week's session. So maybe, I don't know what everyone else thinks as far as like how much should go into each bite, but maybe making it digestible in a way that people can go at their own pace may be the way to go.
Thank
I
you.
think, yeah, that's all I have for right now.
Yeah, that's super helpful. And one of the things I agree. I think it would definitely make sense to have recorded videos, maybe with like timestamps of like each like portion of the notebook that we go through, and then we could put those up for people to walk through on their own. And then also, I guess so. As a bit of background for the general session next week, we will also have a PowerPoint at the beginning, just in terms of like a high level overview of what machine learning is, like clustering, regression, classification, kind of just like a general like sense of like what is machine learning for people that may not be as interested in the code and actually implementing these themselves, but rather just want to kind of understand what this term they've been hearing for some time is.
Yeah, I think, oh, one other thing before I forget, I think you need to separate out the place where you generate the data, because I don't think people will fully understand that in the amount of time that you explained it. Like I knew what you were doing, but I think you should just separate that into a different notebook.
Got it. Thank you. That's a good point. Anyone else? I'm eager to hear from as many people as possible.
Yeah, I've got a few comments.
Sure.
So this is really cool, first off. Thanks for doing this. And one thing I was wondering about at the start was using Colab. I'd never actually heard of that. And in the chat, we heard that you get the Google TPU to do it. But are there, something to cover would be, are there any other benefits to doing it in Colab versus locally? You mentioned the privacy situation, but maybe speed or iterations or any of that type of stuff could be mentioned.
Okay.
The big question I had while going through this, and I imagine it would be covered in a future lecture, would be how to determine if the data is underfit or overfit, especially when you don't have that ground truth.
Yeah.
So, you know, it's easy to adjust alpha to make it look perfect, but if you don't have that blue line, that gets tricky.
Exactly.
And then a thought I had while Adriana was talking and what y'all said was, as you go through the code, I know you'll have to make some adjustments if you were to do this on a different model, say, I don't know, logistic regression, like any of the other models, y'all know them. It might be useful to point out in your code, like at this line, this is where you would change this if you wanted to do a decision tree rather than regression, or, you know, that kind of an idea, just to interject a little bit of the coding side with the usage. That could probably be commented in. I don't know that it necessarily needs to be verbalized while you're teaching it. And then just the last thought for I know you've got this other session on the testing and training splits. For time's sake, I feel like if I didn't know any of this stuff, I would feel like really overwhelmed, especially because like most people haven't even seen coding before, right? So you may want to just stick initially and say like, do a 80-20 split or something like that. Just, you know, throw it out there as like, generally this is the accepted level. If you don't get those 100 other patients, if y'all are interested, we have a supplemental notebook that'll talk you through a little bit more of the fine details of that. I think that would be appropriate from my perspective. But really good job overall. I'm very impressed.
Thanks to y'all for the feedback. Anyone else?
Yeah, I'll just echo kind of what Daniel said it felt like sometimes there was like a lot of code on screen and like you're trying to talk about the theory more than the code, but it kind of just sent some mixed messages sometimes about what I should be like reading exactly. But no, that was really great. As someone with a little background, I didn't like feel completely lost, even though it's been a while. But yeah, no, I thought this was at a good like level for me, so I was happy with the content.
And I think maybe if you just shared the stuff ahead of time so that someone could look through the notebook, then
Yeah,
it'd be easier for the people that don't know the coding as much.
and I would have really liked to have like had it in hand at the same time as you were kind of running through it, but
Those, I think, great points. I think, do you feel like, imagine this was in person and imagine you did have the notebooks in hand. Would the material be more tractable? Would the pacing be more tractable? Is this a function, is some of this a function of Zoom, or is the material really just maybe too deep to dive into in a first or second session? Is ultimately what we might have to struggle with.
I don't think it's too deep. I think showing this example of how it works from the start is a really cool way to highlight some of what machine learning can provide that you can't do otherwise. I know that if someone was to then take this example and try to put it on their own data, they would run into some issues that you didn't touch on, but that's just par for the course with an intro session. With CodeLab, you don't have to set up your system at all to run any of this, right? It's all in the browser.
It's all server side. So one of the benefits of CoLab is they have a standard library set. So I know that if it works on my computer, it works on yours, right? We were going to do this with Jupyter, but some of the, you have to make sure the libraries align, and if someone gets a different distribution, then it won't run. So
yeah, I like that a lot. Then using CoLab, send the link out ahead of time, and they basically can just click through as you do it. If you were trying to set up Jupyter and type it all out, that would be very complicated.
So that's very helpful. I'm getting, so correct me if I'm wrong, but I'm getting a message of sending the notebooks out maybe like Wednesday or Thursday for a Saturday session might be a good idea.
Yeah, I think that would be a good idea. I do worry when you send out the notebooks. Like I didn't notice if they were commented to like allow people to kind of go through it on their own. Do you think that they're ready for that?
The answer is no. At least not the wide backgrounds that we're seeing with folks, but the goal is to, I think it's a good, the goal is to not necessarily have like 50 notebooks, not to like sequentially go through them, but to have 3 or 4 concrete notebooks that we spend multiple sessions on, multiple workshops on. So I guess, and feedback on this would be very much appreciated. The notebooks could be, maybe should be overwhelming the first time you see them, and then and then we'll be iterating through them over multiple sessions. That combined with the interactive widgets, plus the fact that you can edit the code and run it, might be an ambitious but hopefully doable way of addressing both ML and secondary goal of teaching coding. Did that kind of address your comment?
Yeah, I think just be honest about that when you send them out on Wednesday. Just say, don't worry if clicking through this feels overwhelming. We're going to go through it, and we're going to go through it at a pace that is, appropriate for like someone who's never seen coding before.
Perfect. Yep. And that is the goal. There is a lot of code here, but the goal is to get folks who have zero coding experience to a place where they can feel confident running. So yeah, thank you. That's helpful. Any other comments, questions, suggestions? we will be sending out the notebooks to y'all today, tomorrow. The link is there, but we'll send it through email so that you can actually click on it. And there is text in them. It's not quite polished yet, and the comments are inconsistent so far in the code blocks. That's going to be the primary work for this week, at least one of the things that we'll work on for this week. So caveat on that. And the second notebook, we can run through if we want to, but I'll give a brief overview. It's just testing training. How do you split your data into a set that you learn a model on, and then how do you then do a test of it? We kind of did it. We implicitly did it in this notebook where we had 100 new magic patients show up. That translates to us having 110 patients originally and we did a training set of 10%-ish. So it's not necessarily super important. It might even be one of these secondary notebooks that get sent out for people to work with, but we cover in a second or third workshop. Any other comments, suggestions, questions? All feedback appreciated?
We'll also be sending a survey after all this in case you guys want to type it instead.
Yeah, absolutely.
I just thought of one small thing. I just typed in the URL, and you may also want to include instructions with how to go from those files to actually open it.
Gotcha.
Yeah.
Yep.
Yeah, and another session that we're planning on having after the general one, maybe the day afterwards, is going to be focused kind of like a TA session for anyone that's interested in installing Jupyter on their local machine and is like running into issues or like just doesn't know where to start. We would aim to help them out with that.
That'd be great.
Do I need to? Okay. All right. So if there's not much more feedback, feel free to hop in or out if y'all want to. What do you think, Avinash and Alex? Should we do train test?
So I guess then just open discussion. I'm starting to wonder if we're not going to include it in kind of as part of the general session next week, then perhaps we could just send it out to this group for kind of offline feedback. Would that work?
Yeah, I've got to hop off, but I'm happy to look at it later.
Absolutely.
See you guys.
Yeah, same here. I do need to go, but I do think that topic is really important. So I definitely encourage you guys to, if you want to share it, I'd be happy to give feedback on it. But I think I feel like that's where a lot of issues start arising in machine learning, and it becomes like this tool where it's like, it sounds like magic and it's amazing, but then when you start applying it to data, you realize you realize the limitations, especially with clinical data. So I'm excited about seeing what you guys have for splitting training sets and deciding on your training set and stuff like that.
Perfect. Thank you. Yeah, absolutely. We really appreciate y'all's feedback. Thank you. So we do, this kind of addresses some of the feedback we have, and maybe this is a little bit more directed towards Avinash and Alex, but we do have a separate notebook that's more basic linear regression. So one of the ideas was, at least with the intermediate session, cover what we just covered and test train, versus the general group. The general session next week, one option was to cover basics, very basic linear regression and test train. So this notebook's a lot more straightforward. It's just linear regression in 2 dimensions, covering what is slope, how does it work, a little bit of interactive slope, noise, samples thing. So it might be worth it to swap this out for the advanced in the general session and also enable covering testing and training. That might be more tractable.
And part of our question that we had been debating on that was whether if we just did kind of simple or like basic linear regression, whether people would kind of come away from the session feeling like they didn't necessarily learn something particularly new. So I guess, does anyone have thoughts on, do you feel like if you were a beginner, came to this session expecting to learn more machine learning, but then just came away with like, a basic linear regression, would that be something that you would it be too little, I guess?
Yeah, we don't want to scare people away, but we want to excite them,
Yeah, I think too. I think when someone said this earlier, I think it's cool to like come out with like an example of why this is neat and powerful, and maybe starting out with just like a basic linear regression is not going to get people excited. But maybe if you wanted to be like, hey, we can do this cool thing, but first let's talk about linear regression. I think that's a good way to kind of like get people excited, but not overwhelm them with like too much stuff going on.
Cool. No, I appreciate that.
Yeah, I think Sam's right. I think giving people a taste of it, but not spending a ton of time on the really fancy stuff, and then saying we're gonna get there, we're gonna show you how to do it, but let's do this first, just as a an introduction, because it's a good. I mean, it is easier to explain things with a linear regression.
Yep. Cool.
I have one idea. Maybe you could go through like a classification problem using the regression. I feel like a lot of people, when they think of machine learning, they want to predict like something about something. Classification problem like sets it up naturally, and obviously you can use a regression model for it, so you can walk through all the stuff you have here, but with that motivation.
Gotcha.
Yeah, that's a really good point. We weren't planning on covering it in the initial sessions, but we could swap it around. So we do have a logistic regression notebook as well, with a classification example that we could send out for feedback to.
Yep.
Yeah,
That's a good
idea.
Thanks, Rob. Yeah, so I think a lot of y'all are hitting on exactly some of our concerns, so we really appreciate it. It might make sense to focus in on these 3 notebooks, send out these 3 notebooks so that people are at least aware of the advanced, the thing that we just covered, the high dimensional regression, but then focus in on Saturday on some very basics of linear regression. So one thing, we don't have to do a formal, I'm not going to try to do a formal presentation of it, but I do want to get y'all's thoughts on this particular widget. And what this is it's a hands-on example with linear regression in the basics of linear regression notebook, where we kind of build up in non-interactive examples what is linear regression, with an example where it's A1C versus lifetime cardiovascular disease risk. I just chose, arbitrarily chose intercepts and slopes based off of what seemed right. Might be worth it to go cite a paper and get a hard number for it. But the whole point of this is, well, we have these data points. How do we then fit a line to this? Because that tells us potentially how they're related to each other. And then we dive into an example where we're kind of in a general way seeing how noise comes in and complicates our ability to do a linear regression. So if we have 0 noise and 2 samples, we're fine. We're completely fine. We will almost always hit the slope perfectly. But the moment you introduce noise is when things become a little bit more complicated. And then how you compensate for that is samples. If you have more samples, then you can actually account for the fact that there's a lot of noise. But if you don't have a lot of samples and you have a lot of noise, then that leads us to the advanced linear regression session that we just had, which is 10 patients, 13 variables. There's noise in the mix of it. We can use regularization to try to figure things out. This notebook might be a more appropriate starting point, so where we cover basics of linear regression in 2 dimensions and then end on a interactive example that, correct me if I'm wrong, folks have never really had, but may help solidify the linear regression base needed to do then the advanced linear regression notebook, which we could do in a second session or a third session. We do want to stress, like, the goal of this is not to be a one-off thing. The goal of this is to be a recurring thing that is open to folks at very different levels of engagement and background. So I guess my concrete question is, would this interactive example with linear regression, simple linear regression, two-dimensional linear regression, be a more appropriate starting point for next week versus the notebook we just went through? Anybody? No comments?
Without seeing all of it, I think it will be
Okay.
like a more approachable thing, because people have prior information about linear regressions. It's not like the first time that they're seeing it. You know, they kind of know, like, and you know, how they could make a linear regression on Excel, except at least I think most people can.
Cool. Okay, that's helpful. That's a good point. I'm just showing you one isolated cell of a bigger notebook. This notebook is in the directory where that will send a link out for sharing. We've really focused on 3 notebooks: basics of linear regression, advanced linear regression, and testing and training. So those, the vibe I'm getting, and I completely agree with it, I think those 3 notebooks alone could be enough for 10 sessions if we just keep hammering them in. And then hopefully folks at different levels, folks with different goals, will be able to then take the notebooks, branch the notebooks, do their own thing with the notebooks, or just say, I'm done with the notebooks, I feel comfortable enough to do this analysis. So I definitely, I appreciate it. And also, we don't have to necessarily answer that question now. I would appreciate if anyone has a chance to look at the basic linear regression notebook after we send it out today or tomorrow. Just any feedback as to whether you think it's more tractable, more digestible would be appreciated. Cool. All right, it's 12:23. Any other comments, questions, suggestions? I think at this stage, with everyone's blessing, we won't necessarily go through testing and training as a notebook. We'll send it out again. I want to stress that. We'll send it out, take a look at it, let us know your thoughts. But at this stage, it looks like we might, there's a way to shape this so that the basic linear regression notebook is all we cover next Saturday, but is covered in a way where we address, 100 new patients show up. Let's see how your model does in predicting those 100 new patients in this simple two-dimensional linear regression. That might actually be a more digestible example. Cool. Anyone else? Any comments? Sam?
I'm good.
All right.
Sounds good. Yeah, so we'll send out the form afterwards, and the notebook links, and look forward to hearing what you guys have to say.
Thank you all so much for spending the time this Saturday on this, and for checking in and coming and visiting. Feel free to send emails to us at any time, any comments, suggestions. The survey can be anonymous, and we'll look forward to next Saturday. Hopefully some of y'all can join us. All right, cool. See ya.
All right, thanks. See ya.
All right. Cool. About right?
Yeah, I think the feedback was super helpful.
We can stop the recording.